like, why is it so important? I'm not skeptical, I just,
Alright,
I was just curious is all.
alright, so this is justification for why lenses work. Because the light will come in, so if I have a lens like this, as light comes in, and there's my normal right there, it's going to bend this way, then it's going to hit here, I got a new normal, and then will bend away. So it basically allows you, and we'll derive the lens maker's formula, but it allows you to custom make lenses in order for light to behave exactly the way you want it to.
Oh, okay, thanks for that. I was just wondering.
And also fiber optics, and we'll hit fiber optics right now. Unless there are other questions? So notice here that when it goes from a higher index of refraction to a lower one, it bends away from the normal. So if I make this light incident like this, well, it's going to bend off like that. At some point, there's going to be this angle at which it hits, in which the refraction is going to be just straight down. It's not actually going to leave the medium. And so if I have some sort of material here with index refraction, we'll just say N, and we'll make this air. So N is approximately equal to 1. What I want to do is figure out what is this angle so that it will bend right along the path there. In other words, if this is my angle of incidence, my angle of refraction is 90 degrees. So plugging into Snell's law there. So I have N sine of theta sub I is equal to, since I'm making air, times the sine of 90 degrees. And what's the sine of 90 degrees?
1.
And so if this is bathed in air, then the angle of sine of theta I is just 1 over N. So water, for example, be 1 over 1.33, which is about 0.75.
Yeah, 49 degrees.
So if I'm looking at a body of water there, anything that comes in under that 45 degrees, so we can take that one step further. So I got a body of water and I'm standing off to the side here, and I'm looking out at the water. Wrong way, this way. Anything that comes in with an angle of 49 degrees, that's going to hit and just shoot right along the surface of the water, and I'm not going to see it no matter how far down I get. I'd have to put my eye right here to catch the stuff at 49 degrees, which presumably will sting. Taking this one more step as we explore this stuff with great enthusiasm. Surface here, I have some object underwater. Light hits it, and I'm basically going to sense it there. So I have something right here, light goes through it, let's say it's underwater for just a visual. Light hits it, bounces off, and eventually that light hits me in the eye. It will appear that the object is there. It's going to appear higher up in the water than before. But the actual depth is here, and just so that we're keeping the same letters that I used in my notes. Oh, object P, and then image Q. Let's figure out what that relationship is. So the distance between the actual horizontal location of the object and where the light actually leaves the water, we'll make that distance D. This angle right here would be the, I'll call it theta 2. So this angle right here is theta 2, and I feel like I need to make this bigger. So if you've got it in your notes, no problem. I'm just going to make this larger. So that distance there is Q, and then P is this distance here. Theta 2 and theta 1. All right. So this angle right here, because this is normal to the surface, that's normal to the surface, alternate interior angles, this is theta 1 here. This angle right here, that's theta 2. This would be the complement of theta 2. And so this is the complement of theta 2, which makes this angle down here theta 2. I can see I got you all riveted. Woo, physics. Letters on a board. All right, let's play around here. I have this length here is P and this length here is D, which I had labeled before, but forgot to relabel. So the tangent of theta 1 is the opposite of the adjacent. So it's the opposite side over the adjacent side. So that's D over P. The sine of theta 2 is the opposite over the adjacent, so that is D over Q. Now, we need to bring in the small angle approximation. We've done it before. What is a small angle approximation?
There's a certain angle where the result is going to be less than 10%.
You got a lot of keywords, slightly wrong order there. Small angle approximation. Anyone else?
Angle is less than 1.
Much less than 1.
Right. The sine of the angle is very close to the measure of the angle itself.
Okay. There's one other piece to it. We didn't use the other piece before, but one other piece to it. If the angle is much less than 1, and that's implied radians, not degrees, then the sine of theta is indeed approximately equal to theta, which is, as Thomas said, which is approximately equal to the tangent of theta. So even though I have tan theta and sine theta, if I assume that this is a small angle that we're dealing with here, in other words, it's deep enough, then this is approximately equal to the sine of theta 1. Let's do our fancy math here. So if I do the sine of theta 1 over the sine of theta 2, that is gonna be equal to d divided by p over d divided by q, which is q divided by p. And using Snell's law, I know that n1 sine theta 1 is equal to n2 sine theta 2. So sine theta 1 over sine theta 2 would be n2 over n1. And so we now have a way of calculating how deep something actually is based upon how deep we think it is. And so that's what they get it to the apparent depth. So we don't get into the interference yet, which is later. Okay. So let's take it one step further. Any questions up to here? So it comes in at some angle, we'll just make this 45 degrees. It hits the water. It then comes down here, so this would be some theta, it's called theta 2. It's gonna hit the mirror, bounce off, hit the air, and then move off. So first off, what's theta 2? Want to work it out?
Be about 32 degrees.
When I put a 1 sine 45, I got a 0.707.
Right.
Yes.
And then divide by the index of refraction of water, the 1.33.
Oh, wait, never mind,
And then dark side at the end. Anyone else get 32 degrees?
I did.
Okay.
1 sine 45 divided by 1.33.
1.33.
This is what I got to.
And then you take the arc sine of that.
Yeah.
Oh.
Arc side.
So sine -1?
Yes.
Oh, okay, now I see.
Okay. All right. So the angle, if that angle here is 32 degrees, what is this angle right here?
32 degrees.
And therefore this angle right here,
32 degrees.
and this angle right here,
32 degrees.
and this angle right here.
Probably about 45.
Yeah, probably about 45. Now, realize the implication of this. if you shine light onto if you have a body of water here, you got a glass of water, whatever it is, you got water right here, and you shine light onto it, yeah, some light's gonna penetrate into it, but is all of it? Probably not. There's a certain reflection. You can see the sun in the water. There's lots of pictures out there where you see reflections off the surface of the water. That's not air, the light coming in, going down to the bottom, hitting the mud, and then coming back up so that you can see it as clearly as you do. So some of the light that hits this is going to bounce off. What's that angle? Yeah. So you now have these two light waves coming in that are slightly out of sync with one another. So the difference between the light is that distance right here. And so if that distance there is equal to a wavelength, then you won't notice. Because that would be like I have one light coming in looking like this, the other light looks like this. But suppose this distance is a half a wavelength. So this one starts, let's see, this is some central axis right here, there's half a wavelength right there. So if the second one is a half wavelength off, what's happening now? And if they're out of phase,
It's destructive interference.
absolutely. And so we now have an interference pattern. So if, and for the lack of imagination, X. So if X is some multiple, well not N, some multiple of half the wavelength, we should get dark bands. Interference, destructive. Now that's sort of a preview of what's happening in a couple of chapters, but that is what's coming up. We've done chapter 35 at this point, and a little bit beyond. How about the quiz on chapter 35? We could have the Monday right before spring break or the Wednesday, week from Wednesday.
Before spring break? Monday before spring break? Does that seem okay with you guys? Wait, is that that's the Monday before spring break, right?
No, spring break starts on Tuesday. Spring break starts on the 16th.
You guys okay with the 15th?
I've got plans for that day, but
Oh.
if I take it Wednesday, Ruth's going into it, and then the rest of us could take it on the Monday.
And I would be okay doing it on Wednesday.
Yeah, let's do Wednesday.
Alright, so
Is that good for everyone?
So the 8th, you have the quiz on chapter 34, the 10th, the quiz on chapter 35. Guys are like, we're done. However, it really does not make sense to start on the lens maker's equation. Yeah, what do we call that? And then Because the Lens-Maker's equation takes probably about a half hour to do. And I'd rather not break that one up in half, because drawing the picture is a little pain. All right,
Alright.
so long farewell, auf Wiedersehen.
I don't wanna stay.
This is there.
Sprechen Sie Deutsch?
Like this here.
I don't. I know a couple of phrases, that's it.